Section 9.8 in our book is the section on power series. Power series are kind of just an extension of what we did with our polynomials in section 9.7. But when we're talking about a series, we know we're talking about an infinite sum. So instead of having a 4th degree polynomial or a 12th degree polynomial, we have something of the form a sub n x to the n, and it's going to go from 0 to infinity. So we have a polynomial of infinite degree. If we have a sub n x sub n, this is called a power series. Also, if we, still going from 0 to infinity, have a sub n and some expression in x minus c to the n power for our series, then this is a series that's considered centered at c. So we had a Maclaurin polynomial, maybe we centered it at 0, but if it's not centered at 0, then we need to take that into account here. So center. When we're looking at a power series, the first thing that we worry about is what's called the radius of convergence. Excuse me. The radius of convergence tells us how far we can go from the center. Right, and then talk how far we can go from the center, C, and be in an interval where this series will converge. We know that not all series converge, and we talked about a whole slew of tests that help us figure out whether they do or whether they don't. But our goal is going to be to figure out how far away we can get from the center and still converge with that series. Sometimes we can't go anywhere and have it converge. Sometimes we have an infinite radius of convergence. Oftentimes it's some finite value. Once we know the radius of convergence, then we find what's called the interval of convergence. Sorry that my handwriting's terrible with this tablet. I don't do very well with it. But once we find the radius, we know how far we can go from the center and still converge. But then I have to figure out what we do with the endpoints. Sometimes those intervals are open, sometimes they're closed, sometimes they're half and half. The main test that we're going to use to determine all of this, oftentimes we'll use the ratio test. It's usually the friendliest test to use. Sometimes we'll use something like the root test if it's set up in just the right way where the root test will help us. But a lot of things come down to that ratio test that we saved almost for last when we were learning about our tests. So if we're looking at power series, our power series, one example might be something like x to the n over n factorial. Okay. Or if you want to look at it as a sub n x to the n, our a sub n would be 1 over n factorial. Now our center here, since I have plain old x to the n power, our center is at 0, if we're concerned about that, as we will be in a few minutes. If I want to figure out where this series converges, again, I said the ratio test is going to be really useful to us. So for the ratio test, we're going to take the limit as n goes to infinity of the n plus first term divided by the nth term, which after we flip it over, looks like this. When we clean this up, notice that our x to the n's go away off the bottom and we're left with a single x on top. If we take n factorial over n plus 1 factorial, we have plain old n plus 1 on the bottom. So this cleans up to be x over n plus 1. Now, this may not have been a very good one to start with, because when we let n go to infinity, I'm going to circle this, be sure that you keep straight your n's and your x's. We're letting n go to infinity. Sometimes this relies on x and sometimes it doesn't, what our limit is. Okay. But as n goes to infinity, anything over to n plus 1 is going to go to 0. Move my black here. Since we got something that's less than 1, then that tells us this series converges, and it converges all the time. It doesn't depend on what x is. So regardless of x, because we got 0 here, which doesn't depend on x, and so I find out that the radius of convergence abbreviate here, is infinity. The radius of convergence is infinity. Because this is always less than 1, my series is going to converge no matter what x is. So we say the radius of convergence is infinity. Then the interval of convergence, this one's an easy one. Also, if it converges everywhere, then for all values of x, we write negative infinity to infinity. Let's look at the series 3 times the expression x minus 2 to the n power. And let's see if we can figure out the radius of convergence and the interval of convergence for this series. Now there's 2 different approaches we can take here. I said we like the ratio test, and it will work for us here as well. If we take the n plus first term, we have 3 times x minus 2 to the n plus 1. If we take the nth term, we have just what we are given in the original problem. And if we start reducing on that, the 3's are gone. N of these guys are gone, leaving us behind with 1, x minus 2 on the top. So this limit, because it doesn't depend on n at all, okay, there's no more n's in this, we're just going to get x minus 2. Now we know that this will converge, that a series converges by the ratio test anytime we get a number that is less than 1. So whatever values of x make this expression less than 1, those will be the values of x for which this series will converge. Anything that makes this equal to 1 or greater than 1 will mean that the series will diverge for those values of x. So if x minus 2 less than 1 is less than 1, then that means our radius of convergence is equal to 1 for this example. Now, if we have x minus 2, that means our center is at 2. And so if the center is at 2, and I know I'm going to move 1 unit in either direction, that means I am looking at the numbers between 1 and 3. I know my interval of convergence is going to be between 1 and 3, and I'm given that this open interval, it will converge. But what I need to figure out is whether or not, goodness, that's a big eraser. I need to figure out whether or not it actually converges when x equals 1, and whether or not it converges when x equals 3. So then I check one at a time on my endpoints. I say when x equals 1, and I plug in 1 for x, I have 3 times negative 1 to the n power. This is an alternating series, okay, or I could look at it as a geometric series, but it's an alternating series where this is my a sub n, and if I let n go to infinity, a sub n goes to 3, which is not 0, which means I diverge for the value x equals 1. Since it diverges for x equals 1, that means up here, if I can get up to there, I'm going to use parentheses. If we let x equal 3 and look at our series that's created, we have 3 times 1 to the n power, or I'm just adding up the number 3 an infinite number of times. Since 3, as n goes to infinity, 3 goes to 3 and not 0, the nth term test tells us that we diverge at that endpoint as well. which means my interval of convergence for this series is the open interval from 1 to 3.